this lab is to apply Newton's second law and gravitational principles to simulate realistic space systems. Newton's second law states that the acceleration of an object is directly proportional to the net force acting on it, and is inversely proportional to its mass. Newton's law of universal gravitation describes the force of an attraction between any two objects with mass in the universe. The parallel and perpendicular components separate the force vector into parts that contribute to the motion. The main results of this lab show that for the first part, the motion of the star was consistent with the gravitational pull of the central object. For the second part, the orbit of the ship was influenced by the mass of the black hole, and analyzed the star's motion to find the net force on the star for all points in the dataset. The net force on the star was assumed to be solely due to the black hole. The system is the star and the black hole is the source. The surroundings refer to everything else outside. The initial conditions of the star's x and y positions are generated based on a seed, which is my Georgia Tech unit. For the second part, I calculated the necessary gravitational forces using Newton's second law to predict the motion of the moon and the spaceship. The system consists of the spaceship, moon, and the planet. The surroundings are everything else. The initial conditions, the ship velocity influences the resulting orbit of the ship, and its a key variable that was adjusted to try to achieve a figure 8 orbit. The initial and final movement were calculated using movement equals velocity times mass. To calculate the parallel component of the rate of change of momentum, p hat represents the unit vector in the direction of the final momentum. Multiplying this scalar by p hat gives the parallel component of the net force. The total vector minus the parallel component gives a perpendicular component. To find the single value of the slightly different values for the black hole, I took the average. In the model, the magenta arrow represents the parallel force, which shows any change in the star's speed. The cyan arrow represents the perpendicular force, which keeps the star moving around the black hole. The estimated mass of the black hole is 1.6 times 10 to the power of 29 kilograms. The initial velocity of the spaceship directly affects how it moves under gravity. The goal is to adjust these values so that the spaceship doesn't crash into the planet or moon. In the calculation loop, I first calculate the force of gravity on the moon by the planet and the ship by subtracting the position vector of the system by the source. Then, I use the law of universal gravitation to calculate the force on the moon by each source and added them up. I did the same process for the net force on the spaceship. The velocities and positions of the moon and ship were updated by applying the velocity update and position update formulas. In the model, the spaceship's orbit is influenced by the moon's movement and the planet's strong gravity, but a figure 8 orbit is not achieved. Sources of error include the finite time step, rounding errors, and the simplification of the systems and surroundings. For part 2, the trial and error basis of choosing the initial velocity and the simplification of the gravitational model for the moon and planet may affect the final results. For the first question, the momentum change is measured from data while the net force represents the physical cause of that momentum change, in this case the gravitational pull from the black hole. These measurements are broken down into parallel and perpendicular, in which the parallel component changes the speed while the perpendicular component changes the direction. For the second question, to predict the motion of the entire system, I would need to compute the gravitational force between every pair of the objects in the system. The most dominant interactions would be between the black hole and the star, because it has the most massive body. Thank you for listening.